Welcome to class. I'm Professor Allen. I'll be your host today. Okay. So, what's that? Save. Yes, I'm save. That's a good idea. File. Save as. Probably get it saved. That way I can save it quickly when it's time. Browse. I don't know. Let's put it in downloads. I always look for stuff in downloads. Class notes. XLSM. Let's call this like variables. Okay, so today we're talking about Chapter 6. The large part of Chapter 6 is variables. So that's going to be the topic for today. So turns out I can't talk and type at the same time, apparently. Variables. Lay it on me.
So a common operator would be like the plus equal sign if you want to add something, which we kind of could use that last.
Stand.
I tried using that. I got a syntax there. I was reading the VB doc.
Aha.
So how close is Visual Basic and VB.NET? Like, would we feel comfortable coding on VB.NET?
Stand by. Let me get a demo up here to answer that question. Sub variable demo. Variable demo. Dim x as byte. We'll talk about different data types today as well. So what you're saying is you want to say x plus plus.
Or x plus 10.
Yeah, x plus equals 10. So the answer is this syntax was introduced into VB at around when VB.NET came around, which was early 2000s. And so it's like 5 years after the definition of Visual Basic for applications. And so that syntax just isn't here. How comfortable would you be moving to VB.NET? Well, the current version of Visual Basic is Visual Basic.NET. And you would be pretty comfortable, but there are some syntactic differences that you'd have to tackle. So
Generally, it's a very similar amount.
yeah, I would say maybe 85% similar. Well, what you're saying is, yeah. So the question is, well, could we do the same stuff that we're doing in VB.NET? And the answer is yes, you can, but you have to instantiate the Excel object separately. So here the idea is we open up Excel and the Excel object is here and ready to go. I can still manipulate Excel from VB.NET, but I've got to just create the object to do it, and then I can work with it. So I really can't do much of the same stuff that I'm doing here, but it's just not native to the workbook. It happens from outside the workbook. Yeah, and as nice as some of these operators are, they're just not available to us. All right. So we're talking about variables. Oh, did I ever tell you about my dad? Did I tell you my dad? I learned to program from my father. Did I tell you this? Oh, it's a longer story than I want to tell you today. But anyway, he spent most of his adult life, as a builder, a general contractor. And then there was a time right around when I was 12, 13, 14, he got a job as a computer programmer. I guess that was back in the day when anyone could be a computer programmer. You're a contractor this day, next week, you're a computer programmer. But I was just old enough to kind of start getting interested. We were starting to get computers in the schools, and it was exciting. And so I was pretty curious. And so, my dad taught me how to program. It turns out my dad was never a very good programmer, and he was never a very good teacher, and the combination was very painful. And I still remember when he was trying to teach me about variables, I just couldn't get it. He kept trying to compare them to pigeonholes, and I didn't even know what a pigeonhole was. And a little tip, if you're going to pick a metaphor, pick one your audience is familiar with. That'll be a big help to getting the point across. So, and actually, I was kind of surprised to find out our author used the same metaphor today. Maybe they were programmers together in former life. My dad he moved to Silicon Valley. He would fly up. We lived in San Diego, but he would fly up Monday morning and fly home on Friday evening for a few years. Maybe they were working at the same company. I don't know. Okay, so, but our author never really explains what a variable is. He uses a metaphor. And I'm going to tell you really what a variable is. And I think it will help you to understand what's going on with these programs quite a bit better. So, there is one place, if we look at the physical hardware of the machine, there's one place that I can put a value to hold it for a while and then bring it back into the processor. Well, there's, I guess, two places. I could do something that writes it out to stable storage. Well, what's the name of that, for full credit for class participation, what's the name of that place where I can just temporarily put a value and then call it back later. Yeah. Yeah, random access memory, or RAM. You got memory in this computer, and that's where we're going to store values. And just not for long-term storage, but just while this program's running, we want to have a value sit around somewhere, and then pull it back, and then add something to it. We're going to put that in memory. And so, let's see, you've got a nice computer there, sir. How much memory do you have in that computer?
I don't know.
Probably 8 gigabytes of memory or something like that. How much is 8 gigabytes of memory? I mean, do you have a sense for how much memory that is? Do you have any idea how big the Book of Mormon is? Like if you were to put the Book of Mormon in memory, how much would it take?
Audio text.
Text. Yeah, just the full text of the Book of Mormon.
100 megabytes.
We have contenders here. 100 megabytes, lower. We'll take 5 guesses, and if you can hit it in 5, we'll give full credit.
5 kilobytes.
5 kilobytes, higher.
5 megabytes.
5 megabytes, lower.
Wow.
2.5 megabytes is so close. It was our last guess. It's about 1.2 megabytes. 2.5. But you were still like more than twice of the real number, so that's not close enough for full credit. Sorry. What's that? Not with the pictures. No, you add the pictures. It gets bigger. You thought we were talking pictures. High-resolution pictures. How high resolution? So high that it gets you to 2.5 megabytes. That's how high. So if you have, let's say, who's got 16 gigabytes of RAM on their computer? Anyone here have a computer with 16? We got a few of you here with 16 gigabytes of RAM. That means 16 gigabytes. That's 16 million megabytes. 16 million megabytes? 16,000 megabytes. 16,000 megabytes. It's 16 million bytes. Yeah. So you could hold the Book of Mormon in memory 16,000 times. 16,000 copies of the Book of Mormon in memory. That's how much storage you have just in memory. That's a lot. That's a whole lot. And so, but that's the place. That's where we're storing these values. So part of what we're going to be talking today is we're going to be talking, well, how do I decide if my variable should use 1 byte or 2 bytes? You've got 16 million of them. Do you care if it's 1 or 2? Probably not. But we're going to talk about the different data types anyway. And part of that is going to be that before too long in this class, I'm going to teach you how to declare 10,000 variables with one statement. And when you're making thousands upon thousands of variables at once, you probably should be thinking, should it be 1 bytes or 2 bytes to be able to use? So we're going to understand it. Okay. And so here's memory. We're going to represent it as a cloud just because that's a fun way to do memory. There's a lot. There's 16 million of these things to work with. Okay. So here's what I'm going to do. I'm just going to refer to one little location in memory. So that's a slot in memory. It turns out that every location in memory, each one of those 16, how many do you have? 16 gigabytes. So 16 million locations where you can put something. It turns out that each one of those, actually, you have 8 bits in each one of those bytes that you've got 16 million of. And so you've got 16 million times 8 little different locations in memory. And each one of those locations has an address. So any value that I put in memory is going to start at a particular address, and it'll take up then several other of those bits to decide how much it takes to store that memory. But every single one of those locations has an address. And it's going to be some hexadecimal address. Well, the address is actually, the typical way we think of it is a bunch of ones and zeros. Just a binary representation of where that bit is. The next one's one more. But we will typically think of these by their hexadecimal representation. How big is it? 16? That's good. So I'll put a hexadecimal number here, my favorite hexadecimal number, which is BA5E BA11. Why is that my favorite address? It kind of looks like baseball. Yeah. I'm not really a baseball fan, but I'm just a fan of a word that's actually spelled by a number. That's kind of neat. So I got some number. I mean, I have some location in memory that is referenced by an address, by the number of where that location in memory is. It is a physical address. If I was to look at that hardware, I could find that address and I could point at the little part of memory that said, I'd take a microscope, I could point at it and say, right there is where that location in memory is. And back in the olden days, when we first started having memory that we could, dynamically assign, we actually referred to these locations in memory by their address. There are two reasons why that's a really bad idea to do today. So we got all these. If you can come up with one of these two reasons, I'll give you full credit for class participation. It has to be one of the two reasons I'm thinking of. So, yeah, go ahead. Yeah, no, it's you. Yeah, it's.
I guess so. I mean, they're not really helpful. Like if I'm looking at a bunch of code.
Yeah. You're looking at the code and you're thinking, what is BA 5e, BA 11? If I'm storing something about a baseball game, maybe, but otherwise it doesn't have any meaning to me. So that's one of the reasons it's bad. The other reason is kind of harder to think of, and that's that, in an operating system today, I could have, 12 or 20 or 100 different programs running at the same time. And if each one of them is asking for a specific location in memory, what's going to happen when two ask for the same location in memory? I'll have one program write the number 6 there, another program write the number 27 there, and then the first program is going to read it. What's going to be there? It's expecting a 6, but what does it get? It's a 27. That's not going to be, that's no good. In fact, Windows and Mac OS 2 will actually prevent that from happening. If a program tries to access memory that hasn't been allocated to it by the operating system will actually terminate that program. It won't just say cut it out. It will kill it. We don't know what you're trying to do, but stop it, and will kill the program. Okay, so instead, the way we do it is our application is going to ask the operating system to say, listen, I need some memory. And the operating system says, well, how much do you want? And it says 2 bytes. And the operating system says, sure, I've got 2 bytes I can give you. And it hands back the address of where those 2 consecutive bytes in memory start. So, I've got these 16 bits of memory. It gives me the address of the very first bit. And then says, there you go, that you're going to get, that memory now belongs to you. As the programmer, I couldn't care less where that memory is. All these bytes, they're just the same to me. It's not like, oh, look at the bytes I got. These are really prime bytes. Operating system gave us some good bytes. No, they're all the same. And so I don't care what the address is. I don't want to see the address. Actually, I could see the address if I really wanted to. There's a way to ask, where is this variable stored? But typically, I don't care. All I want to say is that, listen, when I refer to this variable by its name, you get me to that same location in memory. And so over here in VBA, if I was to declare x as byte, I'll use a more descriptive name than x. Why don't we call this department number, D-E-P-T-N-O, caps lock, D-E-P-T-N-O. So I'm declaring a variable, and I'm giving it a type. We'll talk about what this type means here in just a second. But what I'm doing is I'm coming in here, and I'm saying I want to make a nickname for that location in memory. And so I'm saying, allocate some memory. I'm going to refer to it by depth no. The operating system is going to give an address to Excel, the Excel interpreter, and then the Excel interpreter is going to make the connection between the name that I created in the code and the physical location of where that memory is. So now in my code, when I say depth no equals department number equals 24, then what I'm doing is I am telling the Visual Basic Interpreter to put the number 24 at this location in memory. Now, it actually stores it as a series of 1s and 0s, but it's going to store the value 24. So any questions here? So what a variable really is, it is a location in memory with its nickname. You think of that, the name of the variable as a nickname. It's a name, it's a temporary name for this location in memory. How many of you got a nickname when you were a kid and it stuck, like you still have it today? Anyone? So yeah, these are not those kind of nicknames. These are nicknames that don't stick around very long at all. In fact, when the program is done running, even when the sub-procedure is done executing where we've created, that nickname goes away. The next time I run that sub-procedure, it's going to ask for operating system for some memory. What's the likelihood that it's going to get back the same block of memory that it had last time for this variable? Really extraordinarily small, that it would end up with the same location in memory. There's no connection between the physical location of memory and the name, except for it happened to connect up there once, and the next time we run this, it's going to ask for more memory. It'll be in a different place. But while that variable is active, the variable is the name and the location in memory. Taken together, that's what a variable is. So we've talked about it as like being a holding place where I can put a value. That's right. It's a holding. What is it? It's a holding place in memory. It's a location in memory where I can store a value, and then the name is just a nickname for that location. Questions? Now, when I declare a variable, I can also declare, I can tell it how much memory do I want to allocate. And I'll give it some more information about how to store the data in that memory. So here's the first type. Full credit for class participation if someone can tell me what are the kinds of values I can put in a variable of type byte. In the back.
You've got 256 total numbers that provide the hold, right?
So the comment is you got 256 different values you can hold. That is correct. Now tell me, give me 3 of those values. That'll be full credit. Just tell me 3 values that I could put in there. Pick 3 of them. 3, 5, and 7. Very good. Full credit for class participation. Yeah. But the point is they're integers. The lowest one I can put in is 0. The highest I can put is 255. If I try to put something outside of that range, it's just not going to fit, and I'll get an error. We'll see the error here in just a second. It seems like a really strange boundary, doesn't it? I mean, I'm okay with the 0, but what's so special about 255? Why don't you make it 200 or 100, or 1,000? Why is it 255? There's a good reason that it's 255. Let's take a look at what it is. Oh, did you want it?
That's a multiple of 2.
It is a power of 2. Yeah. It's also a multiple of 2. But it's a power of 2. Okay. So you're right. Everything is stored as a series of 1s and 0s, and so ultimately, everything's got to get translated into binary notation. So let's take a look. We've got this value 24 here, stored at this location in memory. Let's take a look at how that actually gets stored. So I'm going to draw this. I'm going to draw this byte into 8 bits. So here's my bits. There's 1, 2. Can I arrow these around? Oh, I can. Oh, joy. Uh-oh. Control Shift Z. Control Y. We'll take 2 at a time. That was kind of fancy. I've got 4. We're almost there, folks. Now they're not quite evenly spaced, but that's good enough. Were you applauding for my... Look at those paint skills. Give that man a raise. Okay, so I've got 1 byte that's really broken down into 8 bits. Each bit then just a 1 or a 0. Now, these bits then they each have a value. And so this first one is the 128 bit. This one is the, what's half 128? 64 bit. Here's the 32 bit. Here's the 16 bit. Oops. The 16 bit. Here's the 8 bit. 4, 2, and the 1 bit. And so when I put a value into here, and I can only put a 1 or a 0 into any one of these, and so to put 24 in here, 24 is going to be 16 plus 8, isn't it? So I'm going to have, a 1 in the 16 slot and in the 8 slot. And that's how, and then the rest would be zeros. This is how the number 24 is stored. It's 0, 0, 0, 1, 1, 0, 0, 0. What does 25 look like? It's 1 more than that. What does 26 look like? What does 27 look like? Are we getting this? So it's just a binary representation of the number. And so the question is, why is the lower boundary 0? We take away all the 1s, what number would you call that? 0. This is 0. And you fill all the 1s up, what do you have? of 128 plus 64 plus 32 plus 16 plus 8 plus 2 plus 4 plus 1 plus 0 if you wanted to add it on. And that's 255. There really is, there's no more room in that byte to put any other value. So that's why the range is what it is. So let's take a look at this variable. So I'm going to come in here. I put that value here. That should be just fine. And now let me try to put in 255. That should be okay. And now let's go one more. Depth no equals 256. We'll run this, and that should give us an error. What's the error? Can you read that from there? Overflow. Debug. Here's a line that we tried to do. It overflowed. You see, this thing was full of ones. I tried to put more into it. What happened? It was all the way full, and I tried to cram one more into it. What happened? It overflowed. It's actually a pretty good name. But unless you understood what's happening here, you'd go, oh, overflow. What the heck is an overflow? I have no idea. That's what an overflow is. You're trying to put something into memory that doesn't quite fit. All right, well, let's come down here and put 0. What's that going to be? 1's okay. Let's put -1. What's that going to be? An underflow? Still an overflow. A little bit weird. But the point is, I'm trying to put a value in there that there's not room to put. I can't put it in. And so that's what that error would be. So that's why all these numeric types have specific ranges that they're allowed to run in. Questions? Full credit for class participation if you can tell me what the next biggest integer type is. It's an integer type. An integer type. Yep. Integer is correct. So let's end this. All right, Mr. Save-O-Matic, that's your turn to say save. Thank you. We'll save. And let's look at the next type. So let's say, oops, -1. Let's put this back. We'll just get rid of that one. All right. Dim. Why don't we do employee number as integer? Okay, so integer is kind of nice because integer has, it takes, instead of allocating 1 byte, it allocates, oh curses, it allocates 2 bytes. So if I had an integer type, I would have twice as much memory allocated. And so what? It probably allows me to have twice as, how many numbers can I hold now instead of 500, what is it? Instead of 256 different values, I could probably hold twice as many, right? No, way more than twice as many, because each time I add another bit, it doubles my capacity. And so now I can actually hold twice as many values. Now it doesn't, but this one doesn't start at 0. Now what we're saying is, listen, you've got all these, like 64,000 of these things. Maybe you want to have some negatives in there as well. And so an interesting thing about the integer type is that when this thing has zeros and everything, when it's completely zeroed out, what value is it? It's not 0. It's negative 32,767. Or 8. Is it 8? Negative 32,768. And so we start counting from there. I put a 1, that's negative 32,767. I put a 2, it's negative 32,766. And I keep counting up until I've got this whole thing filled up with 1s, except for the very last location. Delete. Delete. And then I have to go one number higher, which pushes my last bit to 1 and zeroes out the rest of these. That's what 0 looks like. And so then I start counting again here, and so 1 would have a 1 in the very first position. I've lost my mouse. Where it is. And so I would just start counting up again. So it's a little bit weird. Some environments actually take 1 bit and they call it the sign bit, which means it doesn't count where the number is. It just says this number is either positive or negative based on whether this is 1 or 0. That's almost what this is, but you get one more number using this scheme because you're not using, you've got a plus and a minus for every number except 0. And if we actually allocate 1 bit for the sign bit, we end up with having either a positive or negative 0, which is meaningless. And so that's the way that this is stored. So your range is basically, it's roughly plus or minus 32,000. And that's why it's got 2 bytes of memory, and so that's what you're allocating. And so let's put some notes here. This is 1 byte. This one's 2 bytes. 2 bytes. All right, save. Let's do another one. Why don't we do the next, full credit if you can tell me what the next largest integer type is. Go ahead. Long. It's an abbreviation for long integer, but it's, yeah, we just call it long. Whoops. Dim salary. I've got to have something long. I'd like to do my salary, S-A-L-A-R-Y, as long. This is now a 4-byte number, and it's roughly plus or minus 2 billion. But it behaves exactly the same as these. I would just double it, and it kind of counts up. Everything is stored the same way. Questions? The question is the difference between integer and long is that long uses decimals? And the answer is no. These ones we've talked about so far are all integers. If I try to put a decimal into this number, I'm not going to have an error, but it's just going to, it'll just round it. It really can be kind of frustrating sometimes. That doesn't stop you until, hey, you try to put something that doesn't fit. It just takes it, truncates it, and moves on. So you've got to be careful about your data types. Okay. Well, now let's suppose, how likely am I to recommend Windows 10? You're kidding me, really? I'm less likely now than I was only moments ago. So let's look at another data type. Can I fit this one in here? I can almost fit this one in. It's falling out of memory over here. Okay. So let's declare a floating point number. So let's dim position as single. This is going to allocate 4 bytes. But now we're going to have a floating point number. So now I can do decimals. Let's take a look at what I might be able to do here. I'm going to reserve some of these right here. So let's suppose that I'm going to store the number 20.25, 20.50. So I'm going to put in here position equals 20.5. 20.5, no, 20.51. There we go. Whew. So how do we actually store 20.51? I'm going to set these aside for just a moment, and I'm just going to start giving the integer representation of this number. Oops. So how many digits do I have that I have to work with over there? In that, to be able to represent that number, how many digits? 20.51. That's 4 digits, folks. This is not a hard one. And so I'm going to represent that number just as, I'm going to forget the decimal point and just represent the integer portion, not the integer portion, but that whole, all those digits as if it were an integer. So 2051. So what would that be? Let's say this is the 1 bit. So that's 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. We're going to need one right. Oh, I lost it. Where was it? It's this one, 2048. So there's 2048, and now I just have to get up to 2051, 48, 49, 50, 51. So I just need 3 more. That's pretty easy because that's going to be these first 2. There's my 2-bit, and there's my 1-bit. And so that is the representation of the number 2051. We're okay with this? The rest where I don't have 1s, those are all 0s. Now I want to say, hey, but there's a decimal point in here somewhere. And that decimal point is 2 digits, the decimal is 2 digits from the right. And so in this portion over here that I've reserved, I'm just going to indicate where the decimal point goes. Where does it go? 2. So in this little block of 4 bits, I'm going to indicate the number 2. Here's a 1, there's a 2. And so that is how that number would get represented. It's called a floating point number. Why? Well, it's because I represent the integers, I represent the digits, and the decimal point floats. I store separately where the point belongs. Yep?
So let's say more specifically, there's 2 digits to the right of the decimal.
So the question is, this is over here in the red part, it's saying, this is saying there are 2 digits to the right of the decimal. And the answer is yes, that's exactly what it's saying. So I'm saying the digits are 2051. That's what this represents. And then this says, take that 2051 and put a decimal point somewhere. Where? 2 digits from the right. This might look a little bit neater if I filled this part in with red. Okay, and so that's the range. I could figure out what the range I could represent just by filling this up with ones, and I've got the precision here. It seems like in VBA, it might do something a little bit trickier where it's not actually, it doesn't have a fixed allocation for how many bytes it's going to use here. It might use part of it to say how many digits are there, and then to say where that is, and then to show it. But this is the idea. This is how a floating point number works. Questions here? Yep?
So is it always use the 4, or is it float and then it can move that part?
So the question is it always use the 4, or is it somehow different? And the answer is I'm not really sure in VBA how it's implemented. And so if it was only the 4, then I would be limited in precision to how many decimal points I could show here. How many decimal points of precision could I show if this is what it was? Yeah, I could do, let's see, this would be the 1, 2, 4, 8. So 8 plus 4 plus 2 plus 1 is 15. And so if that's what's blocked out, I could say I got up to 15 possible places past the decimal point that I could have digits. But I'm not sure if it does something more sophisticated than that. This is a pretty simple way to think of a floating point number. My hunch is that it does something more sophisticated because no one ever prints exactly what the range is. It's like the range, how big you can go, depends on how precise you want to be. And so they're probably doing something that allows that to fluctuate more than just 15 digits. All right.
Save.
Time to save. Thank you. What's that?
That's a good thing I'm here.
Yeah, it is. All right, so I'll just call this one position 2. And the other type, we got one called single. What's the other one? Married? No, double. And the double precision floating point number takes 8 bytes. And it's more of the same. It's just bigger, but same idea. Questions here? Go ahead. So how big can single get? I think it really depends on how precise you want to be. So I've shown this as kind of a fixed 4 bits that we use to indicate where the decimal is. And I don't really think that's the way it is. So I think we use a portion of it to say how many bits are used to show the decimal point, and then one that shows that. And so what that means is how big it can be depends on how precise you want to be. Double is, yeah, double takes twice as much memory, so it's way more precise. It's either way more precise or it's way bigger. Okay? All right, there's another type that's really similar to this called currency. Whoops. Let's dim my salary. We're going to use currency. Let's dim my salary. My salary as currency. Currency uses kind of ideas from both of these. 8, and this is currency is 8 bytes as well. But currency is a fixed point number. Single and double are floating point numbers. Currency is a fixed point number. Currency is always stored to 4 decimal places of precision. As a result, we don't have to take any memory to let us know where the decimal is. It's always stored at 4 decimal points of precision. And so if I want to store the value 1000.1, then it will actually get stored as 1000.1000. So we're going to use those 4 decimal points. We're going to use those 4 digits past the decimal point. They always have to be filled in. So if I have less than 4 digits, it gets padded with zeros. But because I don't have to keep track of the decimal point, it actually lets me say, well, I don't have a whole lot of precision here, but I've got fixed precision, so I can get kind of more bang for my memory buck out of it. So, we could figure out what the range for this one is, because it's just going to be 8 times 8, 64 minus 4, 60. It's 2 to the 60th. Probably plus or minus, so cut that in half. So 2 to the 59th. That's a pretty big number. What is it? Anyone know? So anyway, the point is, if you need a whole big numbers, currency is a pretty good one to do it. Even if they're going to be whole numbers, currency goes huge. All right. So next type. Those are our numeric types. Oh, there's another kind of numeric type that really bears some discussion. So let's dim one called date hired as date. The date, I think, takes 8 bytes. I'm pretty sure of it. Now, so the date type is going to be the first type that we've looked at that when we give it a value to store, it stores something vastly different than the value we give it. Here, we tell it to store 5, and it has to store that 5 in a binary representation, but it's still 5 in binary. We're going to give this thing a date, something like this, date hired equals and let's put a date here. 1/15/2016. Let's do it like that. First of all, let me make sure that works. I think it works. All right. So we gave it this collection of characters, and we could print that out. Debug.print. Debug.print. I'll put a label here, date hired, colon space, and then I'll put the value of the variable. All right, so if I run this, you might think that actually stores in memory 1/15/2016, but it doesn't. What it actually stores in memory is a number that corresponds to that date. Let's see, I'll do that, and then I'll print the number as well, CDBL of date hired. There's a whole set of functions that will convert from one data type to another. But this one will let you see how that really gets stored internally. Oops. So that got stored as 42,384. Why? Because it's 42,384 days from the day that we started counting the days, which is January 1, 1890. No, it's December. Is it 1900? I don't think it's 1900. Let's just ask for the date of the first day, day 1. Question mark, date. Oh, C date. So day 0 is like 12:30. It's a weird place to start, but that's where it starts. So day 2 apparently is January 1st, 1900. It's really weird because if you ask day 0, it thinks you must not be talking about a day at all. You must be talking about a time. Day 0. And so it like omits the time, omits the day, and gives you a time instead. Yeah. You want negative 5,000? That should take you to about the time of the French and Indian War. Oh, no. Negative 50,000 will take you to the French and Indian War. There it is. Right at the tail end of the French and Indian War. Great times. Good times. Good times. You know, what if you wanted it to be like, you know, in the afternoon of that day? Well, decimals are now portions of a day. So that should be halfway through the day. You want to go a little bit further than halfway through the day? There's noon plus 26 seconds. So dates are really stored just exactly like double precision floating point numbers. It's just that when we display them, it says, oh yeah, I know I got a number under here, but my poor human up here won't understand what I mean if I say negative 50,000, 5,003. And so it's going to change that to a human-readable format. Everything gets stored as a bunch of ones and zeros. And so if we have a data type that's going to show something different, we have to have some rule to map between the ones and zeros up to that other representation. And that's the way that dates do it. They say there's an epoch date, and we're counting either forward or backward from that date to have specific times. Time to save. You're right. You're earning your full credit points. You got the feeling I was kind of wrapping up the date. You did. You were right on time. Yeah. Oh yeah, he's there already. He's good. As long as my battery makes it. We got 48 minutes. Oh, we're in good shape. Okay, so another type then that stores as a number but converts it into something else. Let's take a look. Let's dim emp name as string star 15. This, incidentally, allocates 15 bytes, or 15 butes. Now let's put an employee name in here. Emp name. So how much memory am I using to store Lehigh here? 15 bytes. How does it actually store it? The answer is, the way this gets stored is through a conversion table called the Ascii Table. American Standard Character Interchange, Information Interchange or something. So this is just a table that says, listen, character number, let's see, we have a capital L starting. Character number 76 is capital L. And so in that first byte, I'm going to store the binary representation that adds up to 76. Lowercase e is next, so the next byte is going to get stored with 101. Lowercase h, the next byte will be 104, and then 105 will be the next one. You see how it works? We just take one number that maps to each character, and we plug it in for each one of those bytes. So that string allocates 15 bytes, and I can put in 15 characters. How many characters does it use? If I only need 4 characters, it still uses all 15. I've allocated that much memory. So like all the types we've talked about so far, I know exactly how much memory when I use this type of string. This is called a fixed length string. Yep. Let's give it a shot. The question is, what happens if I put something longer than 16 characters? N-E-P-H-I, Nephi, R-L-E-H-I-S-L-E-H-I-S-O-N. I'm not there, am I? What's a good Jewish name? Jacob. Did I get there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, we're over by 4. So let's run that and then print it. What do you think is going to happen? There are 2 options. 3 options. 1, it's going to truncate. 2, it's going to have an error. 3, it's not going to know what to do, so it'll print blank. Who votes for truncate? Who votes for error? Ah, we're equally split. That'd be a good test question. Print emp name, E-M-P-N-A-M-E. The answer is truncate. Bloop. So no error, but just printed Nephi Jacob Lith. Yep.
I'm not sure why you would do the fluid 15. Why wouldn't you just dim it as string?
So there's a way. This is creating a fixed length string. Why not make a variable length string? Then you could put whatever you darn well please. Well, up to 4 gigabytes in length. If you want a string longer than 4 gigabytes, it's like the Book of Mormon 4 times. I'm not sorry, 4 megabytes. No, it's like the Book of Mormon 4,000 times. Yeah, then I'm not sure what you do, but that's a long string. Yeah, so the reason is, we'll talk about the reason right now. Let's dim last name that way. Dim last name as regular old string. How much memory gets allocated when I execute this, or when this line gets interpreted? It gets processed. It doesn't actually execute, but it processes. Here's a trick. It doesn't allocate any memory. With a variable length string, no memory is allocated until I put a value into it. So let's put in Nephi's last name. Last name equals L-E-H-I-S-O-N. How much memory gets allocated? 1, 2, 3, 4, 5, 6, 7. 11 bytes gets allocated for this. We allocate 4 bytes of overhead that just tells us how long the string is. And then, so this is going to say, in those first 4 bytes, we are going to store the number 7. And then they're contiguous bytes. They start there and they all go together. In the next bytes, then, we're going to store the characters that spell out Lehi's. And so the reason that you don't use, the reason that you might allocate something as specifying that number of bytes is because you don't want to incur the 4 bytes of overhead that it takes to do it. So if I'm declaring tens of thousands of variables that need to be 1 character long, I would declare those as string 1 byte. I just don't want the overhead in that case. But you really have to be declaring a lot of variables before that's a big deal. And so almost always the strings you'll declare in this class and in general use are going to be these variable length strings. Questions here? So again, these get stored as a bunch of numbers, but it just gets translated back as we come to look at it. Yeah?
So, how do we actually use that in a situation? I mean, that's all just
Little examples that you wouldn't actually really use. So which one do you want to use? I will give you one example, my child. Which one do you want? Which data type do you want to see in practice?
go with the date.
The date. So it could be that what I'm going to do is I've got a bunch of data here in my worksheet, and I'm going to chart some of it, but not all of it. And so I'm going to ask the user to specify a starting date for the chart. And so I would come in here and say, I'll call it start date. Let's dim start date as a string. No, as a date. And then start date. That's the start date. S-T-A-R-T, thank you. Start date equals input box. Input box. Enter the start date. Debug.print start date. So now when I run this, it's going to say, hey, give me a start date, 2/3/14, and then that value will get written into that date, and here it printed out the value. You'll notice that I typed in 2/3/14, it converted it to a date, so it knows exactly what I'm talking about, and when it printed it back out, it used its standard format and printed it as a 2014. So, yeah, why would you do all this stuff? And that's the reason. We probably wouldn't declare all these, but if I need to hold a value to then decide what to do with it later, that's exactly what I would use it for. All right, so those are strings. The next type, while we're on variable length data types, we now have the great granddaddy. Oh, before we get to that one, I want to do this one earlier. Darn it, forgot it. Let's dim is married as Boolean. Boolean data type is a kind of a strange one. Well, the name is strange. Just say it. Boolean. Boolean. Who comes up with a word like that? Boolean. It's named after a guy named Boole. George Boole? No, I can't remember. He's some mathematician that did a lot of work with true-false values. I see people heading out to Wikipedia to find out who was it. So, yeah, when you find out his name, tell us his name. And if it's George Boole, I get full credit for class participation. Is it George? Is he 1800s or 1700s? 1800s. So, he did, a lot of work with, defining different kind of logic. Boolean, what's called Boolean logic. True and true, true not true, true and not true, that kind of stuff. Okay, so this basically holds a true or false value. So there's only two possibilities that I can put in Boolean. How many bytes of memory do you think it takes to store just one or the other? How many bytes? How many bits could I do that with? 1 bit. Now, it turns out we don't allocate anything less than a byte. So how many bytes do you think it takes? You'd think, but it's 2 bytes. 2 butes. 2 bytes. Why is it 2 bytes? This is really kind of interesting. Let's take a look. Maybe I'll just look at this one here. So I'll say, print true, and it prints true for me. But now let's say true equals true. What do you think? That true or false? That is true. How about true equals 20? True or false? False. How about true equals -1? True. So it turns out that internally, true is stored as a -1. I guess that's why we don't do it with the underlying single byte, because byte we store only 0 through 255. Why didn't they store true as a 1 instead of a -1? You could have saved a byte. I don't know. Well, maybe true equals 1 too. What do you think? No, it doesn't. The only number that true equals is -1. The only number that false equals is 0. So false equals 0 is true. So internally, this is stored as a -1 or a 0. Interestingly, if I was to evaluate something here, like say if true, then if true, then print the time. Okay, so that's true, so it prints the time. And of course, if we put false, it won't print the time. If we put 0, that evaluates as false, and so it doesn't print the time. If we put false or 0, that's fine. If we put -1, it will print it, because that equals true. But it turns out any non-zero number will get evaluated to true when I'm looking at an if statement. So, in a sense, you want to say 0 is false, but for all practical purposes, true is any other number besides 0, although internally it is stored as a -1. So here's another situation where we store a number and we display something different when we ask it to print out the value that's located at that location in memory. Question on the Boolean data type? Yes? Seems strange, doesn't it? You could do it with 1. You could even really do it with a single bit, but that's just the way it is. It's been something that's caused me no small amount of consternation and ponderance. Other things keep me up at night, but not this one. Yeah. Okay. Now, there's another variable length data type. The Boolean is a fixed length data type. There's another variable length data type. Dim any old thing as variant. Whew. Variant is magical and wonderful and hideous all at the same time. How much overhead is required for a variable length string? 4 bytes. How much overhead is required for a variant? 22 bytes. 22 bytes that we just use to manage the data type. But what a variant does, it behaves the way you treat it. You put a date into it, it behaves like a date. You put a string into it, it behaves like a string. You put a floating point number into it, it behaves like a floating point number. So usually about this time, some people are thinking, kind of like to have the last hour of my life back because everything's going to be variant. And I'm going to say, yeah, but you're using 22 extra bytes every time. And you say, I got 16 billion of them. I'm good with using an extra 22 every time. But here's the problem. The variant type has a very sophisticated set of rules that it uses to decide how to do how to behave. And they are, and believe me, you don't know what those rules are. And you will get very unexpected behavior if you just use the variant type. And so the rule is, if you know the type of data, pick the right data type and use it. What's an example of something that would look a little bit odd? Let's just do this. We can see it here without actually running it through a data type because the rules are the same when we're working with numeric constants. What do you think? Do you think that a quote 3 equals a normal 3? If I think about how a normal 3 is stored in memory, what does it look like? It looks like a 1 here and a 1 here. How does a string 3 look when it's stored in memory? String 3 right here is 51, so that's going to be 32 plus something else that equals 51. It's going to be a bunch of 1s over here. So does it look anything like itself? These two look anything like each other in memory? They don't look remotely similar. So do you think they're equal to each other? The answer is they're equal to each other. So, and this is the kind of logic that the variant type is going to employ. It's looking at that and it's going, that's a 3, and that's a 3, sort of. Yeah, that's the same. Even though in memory, it's not even close to the same. So how about this? How about 3 plus 3? What's it going to give me? 2 options here. What are they? 6 or 33. Which one do you think? Do you see what I mean when I say you don't... Whoops, that's not the right one. That's going to be 33 for sure. This one. I don't even know. And I've done this example before. It's either going to be 6 or 33. Oh, that's 6. That seems to kind of make sense. How about this? If that was 6, is this 6? Let's vote. Who says 6? Who says 33? 33. Okay? And the reason is, it's looking at this and it's going, that's a string, 2 strings, stick them together. This plus will mean something different depending on what operators are applied to it. Here it goes, oh, that's a number 3. Now I got a string and I've got a number. Which way should I go? It's got a rule that says, go to the number. If you can, go to the number. So you're going to end up with that kind of behavior when you're using the variant. It's going to behave how you don't expect it to behave. So use the correct data type, and you'll save yourself a lot of headache. Questions here? Yes? Oh, is there a default data type? If you say dim and don't give it a type, yes. The default data type is variant. Now the whole idea is we don't know what you're going to do with this thing, so we're going to use the most flexible data type. And variant is the most flexible data type. All right, we got 8 minutes. There is one more type, and this is one that will make your head hurt. So if you, maybe we should have done it first when you were fresh. Of course, first was 3 o'clock. You were not fresh by a long ways already. Or was it 3 o'clock? 3:30. 3:30. Okay, stick with me on this one, folks. If you're checking your email, finish off that message and come back to me. let's look over here in memory, and let's define a more rigorous kind of structure. So instead of having a variable, I am going to represent an object. An object, see, all these variables we've done so far have been nothing but a single value. An object is going to allow me to have multiple values, right? And we called those values properties before. So suppose this is range A1. It's got all kinds of properties. So one of those properties is the address. One of those properties is the value. One of those properties is the formula. Let's go ahead and kind of put these in here. So this is a complex structure in memory. And it's got several properties. It has an address. It has a formula, and it's got a bunch of others. And then each one of these locations can have a particular value in it. So the value here I'm going to put is 5. And so this would be the value 5 is sitting over there in range A1, and we're keeping track of this by putting A1 here. All right. It turns out I can create a variable that's referred to as an object variable. Here's how it looks. I'm going to come in here and I'm going to declare that variable. I'll call it my range. Dim my range as object. When I declare a variable of type object, how much memory gets allocated depends on my operating system. If I have a 32-bit operating system, 32 bits or 8 bytes gets allocated. A 64-bit operating system, I get 8 bytes of memory allocated. It's just enough memory to store a memory address to another location in memory. And depending on whether it's a 32-bit or 64-bit operating system, memory addresses are longer or shorter. And so this is well, probably whether it's a 32-bit version of Excel or not. But so this is, so let's say I declared that variable, which I called. So it's going to have some, it'll have some address, whatever it is, I don't know, but I'm going to go ahead and put the name for it out here. I called it my range. And so my range is just going to hold a location, a memory location where something else is in memory. And what I would like to do is I would like to put the address where this, come to me, mouse, where are you? I would like to put the address where this object begins in memory. Now, I'm not going to actually write out what the address is, but that's what would be stored here, that address. But I'm just going to think of this as a reference to that location. And the way I connect up, the way I say, go find the address where this object is and put it into this location in memory is something we've actually done already. But we haven't done it. I haven't really explained it to you. Let's see what it looks like. So if I want to connect this variable onto range A1, I say set my range equal to, and then something that can figure out what range A1 is. This statement here binds the object variable to the object. Once I've done that, if I refer to the name of this location in memory, the Excel interpreter is going to go, oh, well, all this is a reference to another object, and so it will forward me to this other object. So now, if I say my range, if I set my range equal to A1, I can now say my range dot value equals 5. And that will put the value 5 into A1 when I run this code. Watch it. There it goes. Oh, and now it's asking for the start date. So this now becomes another name, another way to refer to that particular object. This can be handy because sometimes I have an identification string as long as my arm to get to specifically the object that I want. And so I can set an object variable equal to that and then just work with a shorter name in my code. There are other things that I can do with it that make it really handy, but that's kind of the first thing that's readily apparent at this point. One more little trick I can do here. And so these really are the main types. Are there any more primitive data types? I'm not sure that I left out any of the primitive types. But every type of object can be named not just as object, but as the kind of object that it's allowed to connect up to. So I can declare this as a range. It's still an object variable. But two things are different about it now. In terms of the memory it allocates and how that works, it's all the same. The difference is, once I say it's going to be of type range, the only kind of object I can connect this variable up to is a range. If I try to bind it onto a worksheet, it's going to say, sorry, it's the wrong type. But the other thing that's kind of nice here is now I can say my range dot, and in my editor, it will bring up the context-sensitive help. It brings up the, what's it called? IntelliSense help. And so that's kind of handy. It knows it's a range, and so it says, we've only got those particular kinds to work with. Questions here? The thing we did not cover today is constants. The book in Chapter 6 talks about what a constant is. A constant is exactly the same thing as a variable. It is a location in memory that I give a name that stores a value. The only difference is that once I give that variable, or that constant, its value, and I do it when I declare it, its value can't change while the code's running. I can change the values of variables left and right. A constant, I don't change it while the code's running. I set up its value while I'm writing it, and then the value it sticks during the whole execution. All right, questions here?
Save.
Time to save. Thank you. You've earned your full credit. Make sure you record it. Homework due on Tuesday or on Wednesday. I will see you then. Class dismissed.